Okay, let's dive into something really fascinating, a kind of paradox in robotics. We can build these unbelievably complex machines, right? But what happens when the plans we give them are actually physically impossible?
I mean, just look at a machine like this. We can design robots with all these super intricate joints and connections. But actually telling them how to move from point A to point B, what the engineers call trajectory synthesis, well, that is a massive challenge. And if you get it wrong, the robot could literally tear itself apart.
And really, it's more than just tricky. A lot of the time, when we use standard methods to figure out the best path for a robot, the simulation spits out a plan that is, well, literally impossible in the real world. The math looks perfect on paper, but reality just goes, nope, not happening. So this problem, it actually has a name. It's called kinematic drift. And what it is this slow buildup of tiny calculation errors in the simulation. Think of it like a rounding error that just keeps getting bigger and bigger until the robot's plan has its parts passing through each other or its joints just popping apart. The simulation looks totally fine for a while, and then, boom, it's describing something that just can't exist in our physical world. Okay, so how on earth do you solve a problem that lives inside the math itself? Well, the answer, it turns out, isn't really about the physics, but about the geometry of the problem. To get what I mean, let's imagine a kind of map. A map of every single possible move a robot can legally make. Just think of it this way. For a given robot, every single valid position and angle for all its parts, it all exists on the special surface. You can think of it as a map of reality. Now, in the world of mathematics, this map has a fancy name, a manifold. The key thing to remember is this. If the robot's current state is a point on this map, it's physically possible. But if it's off the map, it's impossible. And really, that is the absolute core of the problem. As the researchers, Bordewalla and his team put it, any drift away from this manifold is what leads to these physically impossible movements. So what does that mean in simple terms? It means the robot's planned path has to stay on this map, no exceptions. Right. So when a path drifts, what's happening is that the plan is telling the robot to be in a position that breaks its own rules. You know, like a metal link suddenly stretching or a joint coming apart. The problem is that the simpler, older methods, they just kind of let these tiny drifts happen at every step. And over time, all those little drifts add up to one giant, impossible mess. Now, for years, engineers have tried to tackle this. They came up with different strategies, but every single one had a major flaw. So let's take a quick look at the old guard, the first attempts at fixing this drift. So as you can see here, these early methods were all pretty flawed. The basic one, it basically just ignores the problem and hopes for the best. Then you have the Baumgarten and PKT methods. They try to correct for the drift, but they do it by cheating. They add these artificial forces that actually distort the robot's true physics. So yeah, none of them were a real solution. But a recent paper came out that introduces two way more elegant solutions. And the best part, they don't have to cheat the laws of physics. This is a genuine breakthrough in how we plan motion for these machines. The real breakthrough here was a total shift in thinking. Instead of trying to mess with the physics by adding weird artificial forces, they said, let's just focus on keeping the path on that map of reality. Period. It's all about respecting the geometry of what's actually possible. Okay, so the first new approach is called the projection method, and honestly, it's so clever. Here's how it works. It calculates one tiny step of the robot's movement, knowing full well that a small error is going to creep in and pull it a little bit off the map. But then, and this is the cool part, it immediately finds the closest physically possible point back on the map and just snaps the path right to it. It's correcting the error instantly before it has any chance to build up, step by tiny step. And this comparison really lays it out. The projection method is great. It snaps the key points of the path back onto that map. But the second method, called the local coordinates method, it's even more precise. What it does is it basically recalculates the path from the perspective of the map itself. So instead of drifting off and then correcting, it just makes it impossible to drift off in the first place. This means the entire path from start to finish is perfectly physically valid. All right, so what does all this fancy math actually get us in the real world? Well, let me tell you, the results are pretty dramatic. I mean, the difference is just night and day. On the left, you've got what happens with that old basic method. The simulation creates a plan that literally pulls the robot apart at its joints. It's completely broken. But on the right, using these new methods, you see that the robot's physical rules are perfectly maintained. The motion is flawless.
And the numbers absolutely back this up. This chart is showing the average kinematic error, basically how far off that map of reality the robot's plan is. And just look at the local coordinates method. The error isn't just small, it's practically zero. We're talking about an error in the trillionths of a unit. That is just an insane level of accuracy.
So, why is this such a big deal? Because this isn't just some abstract academic exercise, right? This breakthrough means we can create way more realistic motion for everything. We're talking better motion planning for industrial robots on an assembly line, physically believable characters in video games and CGI, and maybe most importantly, it leads to safer, more efficient, and more reliable autonomous machines. Think about a robot like this one, with these omnidirectional wheels. The physics of how these wheels work puts really strict rules on how the robot can move. You can't just tell it to go anywhere. Using these new methods is what makes it possible for a robot like this to follow a super precise path without the wheels slipping or skidding or, trying to violate the very laws of its own design. So by making sure a robot's plan never, ever leaves its map of reality, we've actually solved a really fundamental problem in robotics. It just goes to show you, sometimes respecting the physical limits of the real world is the key to unlocking incredible new possibilities in the simulated one. So it really leaves you wondering, now that we can perfectly simulate a robot's physical reality, what's the next impossible problem we're going to solve?